Check one. Check one. Check one. Right. Good evening, everybody. Back again with our MCQ night session after finishing a week thing yesterday. After finishing our chemistry night. Huh. Before we start, confirm me from your end. Is all the DOs perfect? Today I'm using a different mic. Tell me, can you all hear me properly? Perfect. Is the sound quality better than the previous quality? If so, just tell me quality kila. Both are same. Is quality. Hurry, today we'll do the session like this and see. We'll do a test run and see. So towards the end, you will get to know. I'll open all the group. YouTube, no any issues. No? Hot, right. Update is this lamai. Now with today, we are finishing off 2020 O-level MCQ paper. Today is the last in MCQ questions. Last in question 30 to 40. With today, 2020 O-level MCQ paper is done. Tomorrow, we don't have the MCQ night. No? Usually Wednesdays, we don't have. So what I will do is, tonight, after the MCQ session, I will post the past paper questions from electrochemistry. Because already we have done electrochemistry in chemistry night. We couldn't practice any questions now. If I put the questions also, the whole day we have to do only electrochemistry. So we didn't touch any questions. Now theory is done. It has gone into your mind. So I will post the past paper question to the groups. Now, tomorrow no MCQ night as usual, but tomorrow take your day. Day after tomorrow also take your day. Do the past paper questions. I'll mainly highlight and tell which questions I'm going to discuss, but you all do all the most of the questions. Most of the question, finish it off. So on Thursday, without starting a new paper, the next paper is 2019 O-level paper. We will keep it a little bit as we didn't touch any structured essay questions until now, not MCQ. I will post the past paper question, not from MCQ, only essay and structured essay. As we didn't touch any essay and structured essay questions, on Thursday, the usual time, night, 10 p.m. to maybe that day it will go a bit longer, 10 p.m. to somewhat time. We will discuss the past paper question from electrochemistry. Until I finish off my planned questions, we will do it. Maybe it might continue until Friday. After that, we will go for the 2019 O-level paper. So that chemistry night, it will be a complete session. We did the theory, revision part is done. Now again, when we do the past paper question from there, from that end, everything will be done. So that's the update. So tomorrow, no MCQ night. Thursday, instead of MCQ night, we will be doing the electrochemistry past paper question, essay and structured essay. Structured essay, no much. It will come mainly in essay. So essay will be doing, right? So you will have some essay practice as well, right? That's the update. So today, no any other nights. No, chemistry night is the only night. Now some fellows are waiting for bio night. Nah, chemistry night done, right? Hari, ehenang lamai, ehenang lamai. Why you all stay one night and you all finish off the bio? Hari, take your review book. Back to our MCQ review session. Take your review book. Send me ready. There was some question, physics night. Last year we did physics night. Physics night. Tute. Some people texted me asking for physics night tute. Already physics night tute, I have uploaded it in the YouTube, right? I uploaded. Go to the description section. I have the tute there. Physics night is night tute is available. Okay. Ready? Get ready with your usual review book. Right. Right. Perfect. 2020 O-level paper, last 10 MCQ question, that is question 31 to question 40. What I observed in this paper is there are two places where they have touched the electromagnetism part. This is electromagnetism part question, question 33, as well as question 38 also electromagnetism part. Some of you have gone wrong there, and 39th also you have made a mistake. This is from biosphere section. That may be because you don't know the proper meaning of biomagnification. Maybe that's the reason. 39th question also some of you have gone wrong. 38 electromagnetism, 33 electromagnetism, as well as this graph. So three main deep discussable questions are there. Electromagnetism 2 and this graph question. Other than that, this 39 biomagnification part I have to do. Hurry. So our order is going to be, first I will discuss 33rd question, electromagnetism. Together with that, I'll finish off 38th question, another electromagnetism. Then I'll finish off this graph question, heat, and then we'll go in normal order. Onnala my 33rd question. Question number 33. Question number 33. Question number 33. Read. A conductor carrying electric current is kept perpendicular to magnetic field as shown in the diagram. Horizontal lines indicate the direction of magnetic field. Direction of force acting on the conductor is. Now we know under electromagnetism, electromagnetic induction lesson, there are three rules you need to know. Three rules you need to know. One, when there is a current carrying conductor, what direction the magnetic field is going to be. To find that actually there are two rules. From that, at least one rule you need to know. Next, when there is a current carrying conductor placed in magnetic field, there will be a force acting. To find that, you have a rule on that rule also you should know. Next, electromagnetic induction. There also you have a rule. That rule also you should know. Now, I know this section most of the students confuse themselves. Which rule to apply where? Listen, I'll summarize those things. Electromagnetism, electromagnetic induction. What are the rules where it is applied? Right. First, if they give you the direction of current. I'll write it in short form. Direction of current is given. They are asking you for the direction of magnetic field. What they are asking, I'll put a question mark. I, current, M, I take as magnetic field. The standard symbol for magnetic field is B. But those symbols are not there in our syllabus. So we will go with M, right. Current direction is given. Current direction is given. Magnetic field they are asking. Then what is the rule you are going to apply? Two rules are there. One, Maxwell's corkscrew rule. Two, right hand grip rule. Any one of that you can apply, but what I usually tell my students is use the right hand grip rule. It's more easier and it's easy to think. I'll write both the rules and keep. Maxwell's corkscrew rule, right hand grip rule. Now these things are there in the book. No point suddenly quickly going and writing it again in a notebook. It's okay to write and keep. But what is important is from this point you put it to the head and keep it. Such that again for the exam you don't need to study these things. Current flow direction given, magnetic field direction is asked. Then two rules are you can use Maxwell's corkscrew rule or otherwise right hand grip rule. What I tell you to use is right hand grip rule. Number two, direction of current flow is given. Direction of magnetic field is given. They are asking the direction of force. Three quantities are there. Direction of current flow given. Direction of magnetic field given. They are asking the direction of force. At that case, what is the rule you are going to use? Fleming left hand rule. Always remember left comes first. When we are studying also, we first study this theory, then only we go for that right hand rule theory. So left comes first. Direction of current flow given, direction of magnetic field given, then there will be a force acting. That force, how to find the direction? Fleming's left hand rule. Next, third one, electromagnetic induction. Under induction section, direction of force given, direction of magnetic field given. They ask the direction of current. This is electromagnetic induction. In electromagnetic induction only, when a force is applied in a conductor placed in magnetic field, a current will be induced. So this is induction. So in induction, what is the rule you are going to use? That is Fleming's right hand. I hope you all know the rules. Yeah, I'm writing and going. I hope you all know the rule. Maxwell corkscrew rule, don't use it. Mainly use the right hand grip rule. What is the right hand grip rule telling us? What's the right hand grip rule telling us? Now put it to the mind. Now put it to the mind. What is the right hand grip rule telling us? If there is a current carrying conductor, on direction of current flow is there. You take the current carrying conductor on your right hand, eating hand, right hand, such that thumb points the direction of current flow. Current is going in that direction, thumb points the direction of current flow. Then your other fingers, your other four fingers points the direction of magnetic field. Thumb, direction of current flow, other four fingers, direction of magnetic field. See, if the current flow is that direction, you take the conductor on your right hand, thumb pointing towards that side, then thumb that side. Can you see your other four fingers are like this? From top, it's coming out of the board. See, it's coming out. Bottom in, top out, bottom in, top out, bottom in. On. That's the direction of magnetic field. Right hand grip. What is Fleming's left hand rule telling us? Now direction of current flow, you know, direction of magnetic field, you know, you can find the direction of force. How? Fleming's left hand rule. Your left hand, you point your index finger to the direction of magnetic field. You point your middle finger to the direction of current flow such that index and the middle are perpendicular to each other. Index direction of magnetic field, middle direction of current flow such that these two are perpendicular to each other. After you adjust these two, you open your thumb. Thumb gives the direction of, see, your index to the direction of magnetic field. Magnetic field that direction, index that direction. Middle to the direction of current flow. Remember, circle and a dot means line is coming out of the board. So current is coming out of the board. So your middle finger should be out of the board. Out of the board. Maybe you can't see it properly. Can you see my middle finger is out of the board? Out of the board. Now you open your thumb. Thumb points the direction of force. Thumb points the direction of force. Thumb points the direction of force. Fleming's right hand rule. What is right hand rule telling us? Now you know the direction of force. Direction of magnetic field also you know. You are going to find the direction of current. Right hand. Same story. You adjust your index to the direction of magnetic field. Thumb to the direction of force such that these two are perpendicular to each other. Then you open your middle finger. Always middle finger is current. Index is magnetic field. Thumb is force. Now you adjust these two, open your middle finger. Middle finger will show the direction of current. Again, you adjust your index to the direction of magnetic field, thumb to the direction of force. Oh no, these two are adjusted. Now open your middle finger. Mehema you don't show, you are not taking a photo there. You adjust your middle finger perpendicular to the others. Middle finger shows the direction of current. If I draw it and show you, now see, right hand, eating hand, index to the direction of magnetic field. On magnetic field that direction, index to that direction. Thumb to the direction of force. Force is upward, thumb is upward. If the force is down, then you turn it down. Now force is up. Now open your middle finger. Middle finger is out of the board. So the current is out of the board. Current is out of the board. Current is out. So remember where what is applied. Current given, they are asking magnetic field, Maxwell's corkscrew rule or right hand grip rule. Apply right hand grip rule. But if you have already studied, if you are firm with Maxwell's corkscrew rule, then use. That doesn't matter. Again, current given, magnetic field given, force they are asking. Current given, magnetic field given, force they are asking, Fleming's left hand. Next, force given, magnetic field given, current they are asking, Fleming's right hand. Set. Keep the things in the mind. Where what is applied? Current given, magnetic field they are asking, right hand grip rule. Current given, magnetic field given, force they are asking, left hand rule, Fleming's left hand rule. Force given, magnetic field given, current they are asking, Fleming's right hand. Okay. Right. Now see, a conductor carrying current. You see what is given? Conductor carrying current. Current is given. Is kept perpendicular to magnetic field. Magnetic field. Magnetic field. It is kept perpendicular to magnetic field. Magnetic field is given. Current given, magnetic field given. Horizontal lines indicate the direction of magnetic field. Direction of force. Which rule? Current given, magnetic field given, force they are asking. Which rule? Y'all tell. Current given, magnetic field given, force they are asking. What's the rule? What's the rule? What's the rule? What's the rule? Current given, magnetic field given, force they are asking. Current given, magnetic field given, force they are asking. On. What's the rule? Fleming's left hand rule. We'll apply Fleming's left hand rule. Those who got it wrong, apply with me. Apply with me. Fleming's left hand rule. Take your left hand. This one. Always adjust the index first. Magnetic field first. That's easy. Right. Magnetic field, that direction. Point your index to that direction. All of you do it. Do it to the screen. Point the index to that direction. Do it to the screen. Index to that direction. Current is going upward, which means your middle finger should be up. Your middle finger should be up. So you can see. I'll change the screen and do it. It's a bit dark. Magnetic field that direction. Current flow that direction. Or index to that direction. Magnetic field that direction. Current flow upward can your middle finger should be up. Now normally a human, Homo sapien, when they open their middle finger will be like this. But you should take your middle finger up. On turn. Now some fellows, when you turn it, this one also changes. When you turn your middle finger, your index should be staying at the same position. You can't change your index. Index should be at the same position. Now open your thumb. You can't see. My thumb is going into the boot. See? It's going into the boot. Again, see? Index that direction. Middle finger, when I open it, it's like this. But current should be up. Turn it up. Now open your thumb. Thumb is into the boot. Into the boot, you have the boot. Perpendicularly into the boot. Perpendicularly into the boot. Now this is not a board, no, this is a paper. What's the answer? Towards the left, wrong. Towards the right, wrong. Into the plane of the paper, perpendicular to the plane. On. That's the answer. Into the plane of the paper, perpendicular to the. That's the answer. Got it? Those who got it wrong? Got it? Sorry? Those who want the lows on. More than writing, what is important is keeping it in the mind. Surely check this the day before the exam. There are some things you need to check the day before the exam. Some confusing points, surely you should check. So this is one of that confusing point. Okay, hurry, perfect. 33rd question done. Next, going to the other electromagnetic magnetism section question. 38. Question 38. Question 38. Right. A strong bar magnet is moved into and away from an insulating wire coil with a large number of turns as illustrated by the diagram. What is the correct observation about the instances of movement of the magnet? What are they talking about? Magnet is moving and coil is there. What is this? Faraday's experiment. Can remember? Can remember a relative motion section? Faraday's experiment. And the electromagnetic induction section. And the electromagnetic induction section. So what happens here? They are saying coil is stationary. Coil is kept stationary. Magnet is moved into and out. When you move the magnet in, there is a magnetic field. There is a conductor. You are moving it. That means you are giving a force. Magnetic field is there. When it is set in motion, you are giving a force. Magnetic field is there. Force is there. What will be induced, Lamai? When magnetic field and force are there, what will be induced? Current will be induced. Current will be induced. Electromagnetic induction. Magnetic field is there. You move the magnet. That means you are giving a force. When force is given to a conductor placed in magnetic field, current will be induced on electromagnetic induction. So when you move the coil, when you move the magnet into, there will be a current. When you move the magnet out also, there will be a current. This direction of current flow depends on the direction of, maybe when you move the magnet into, there will be a positive current. When you move the magnet out, away from the coil, there will be a negative current. When you move the magnet into, there will be a positive current. When you move the magnet out, there will be a negative current. If so, the current induced is DC current or AC current. Current induced is DC or AC? Guaranteed AC. Why? When you move the magnet into, you have a positive current, a certain direction current. When you move the magnet out, there is negative current, another direction current. Current is alternating the direction. If current is alternating the direction, that's the AC current. AC current is produced. Nothing big. What will happen? When you move the magnet into, maybe the current will flow in one direction. I take it as positive current. When you move the magnet out, current will now flow in opposite direction. It will flow in opposite direction. I take it as negative. Now think, when you move the magnet into, let's take there is a positive current. When you move the magnet into, let's take there is a positive current. Current comes there, current goes through the bulb. Will the bulb work? Will the bulb work? Of course. For bulb, direction of current doesn't matter. Whatever the direction you give the current, bulb will work. Bulb is working. Parallel connection, current will go here. Current is first coming to the arrow side. If current comes to the arrow side of a diode, if current comes to the arrow side of the diode, diode get forward bias. If it gets forward bias, diode will work or doesn't work? It will work. Now this is a light emitting diode, LED. Will the LED light up or not? Will the LED light up or not? Of course, yes, it will light up. Remember the shortcut. If current comes first to the arrow side of the diode, diode will work. If current comes first to the arrow side of a LED, LED will work. One LED is working. One LED working. All right, one L working. Parallel connection. Current will also go here. current is coming to this LED, but first it is coming to the gate of the LED. Gate of the LED. Now tell me, if current first comes to the gate, will the diode work? Oh, it won't work. Remember the shortcut. If current comes to the arrow first, it will work. If current comes to the gate, it won't work. Reverse bias condition. Now this is a LED. Will the LED light up? Oh, no. So remember the shortcut. Current first to the arrow, it will work. Current first to the gate, it won't work. This LED won't work. Only one LED is working. That is when you have a positive current. That is when you have a positive current. Consider the next situation also. Consider the next situation also. Now let's say you are moving the magnet away. When you move the magnet away, now the direction of current flow will change. I will take it as a negative current. Before current was coming in this direction, I took it as positive. Now it should come in the other way and negative current. Now your turn. Current comes there, current goes up. Will the bulb work? Of course, yes. Direction of current doesn't affect the bulb. Bulb will work whatever the direction you give the current. Keep that in mind. There is no forward bias, reverse bias in a bulb. Bulb will work in whatever the direction you give the current. Only it needs a current. Bulb will work. Bulb is working. Parallel connection, bulb will also go to this branch. Now your turn. Current is first coming to the gate. Will the LED work? One LED not working. One LED not working. But consider the other LED. Current goes there, current goes there. Current is first coming to the arrow. Will the LED work? All answer. Current is first coming to the arrow. Will the LED work? It will work. This LED will work. One LED works. One LED doesn't work. Now consider both the scenarios. At both the scenarios, bulb is working, one LED is working. At both the scenarios, bulb is working, one LED is working. Bulb is working, one LED is working. Now go to the question. A strong bar magnet is moved into and away from an insulated wire coil with a large number of turns, as illustrated by the diagram. What is the correct observation about the instance of movement of the magnet? In both the instances, both the bulb and two LEDs light up. Both LED won't light up. This is wrong. Second, in both instances, the bulb lights up and only one LED lights up. Correct or wrong? That is correct. Third, the bulb and one LED light only when moved into the coil. Even when you move away from the coil, bulb and one LED lights up. See, the bulb and one LED lights only when moved into the coil. When you move it away also it lights up. So that this is kind of partially correct. But due to that only word, this is wrong. Fourth answer, the bulb and one LED lights up when you move away from the coil. No, only away and away. When you move it in also, it will light up. So that's also wrong. Answer is answer. Understood? It's a connection of electronics and electromagnetism, electromagnetic induction section. Have a simple section. Okay. Now, what are the things you should keep in your mind? What are the things you should keep in your mind from this section? What are the things you should keep in your mind in question number 38? When the direction of the force changes, what happens to the direction of current? When the direction of force changes, what happens to the direction of current? It also changes. You move the magnet into, current is in one direction. You move the magnet out, current is in opposite direction. So direction of the force changes, direction of force changes. Direction of current also changes. Sorry? As well as keep in mind, if direction of magnetic field changes, if the direction of magnetic field changes, then also direction of current will change. So basically, direction of current depends on two factors: direction of force, direction of the magnetic field. Open the mouth and tell loud. Direction of current depends on two factors: direction of force, direction of magnetic field. Where? In electromagnetic induction. That is point number one. What is point number two? We understand. What's the point number two? We understand. One, you have a diode. It can be even LED, doesn't matter. If current comes in arrow side first, if current comes to the arrow side first, can this current go? Current to the arrow, can it go? Of course, yes. Forward bias condition. Meanwhile, if current comes to the gate first, if current comes to the gate first, now can the current go? Reverse bias. Those are the important points. Those are the important. Right. So will the brightness of the bulb high when the magnet is closer? Now you can't tell it depending on the location of the magnet. You can tell it depending on the speed of the magnet. If you move the magnet faster, brightness is high. If you move the magnet slow, brightness is slow. Can I get the pre-screen? Okay. Only give the force and current and ask for magnetic field. There is no theory like that. You can't give force to current and create magnetism. There's no theory like that. So you can't find the law for that. The new t-shirt. Nah, this one we printed for last year. For the last year coordinators, this was the t-shirt. Hurry. Right. We'll do the question. The main tough questions will be done. Heat question. Super question. Graph based question. Under normal atmospheric pressure, a PO block of ice at minus 10 degrees Celsius was heated at a uniform rate until it was turned into liquid water, and then for some time it was blah blah thing. Sorry, right. Basically, they are talking about state change. Basically, they are talking about state change. What you should know, when the state is changing, listen very carefully. When the state is changing, when the physical state is changing, solid to liquid to gas, when the physical change is physical state is changing, remember, temperature does not change. When the physical state is changing, temperature does not change. Correct? No? Melting point of ice is 0 degrees Celsius at 1 atmospheric pressure. Melting point of ice is 0 degrees Celsius. That means for the ice to melt into liquid water, temperature should be 0 degrees Celsius. State is changing, temperature is 0. Is the temperature changing? Boiling point of water is 100 degrees Celsius. What does that mean? For the water to convert into vapor, water vapor, the temperature you should give is 100 degrees Celsius. Now, during that conversion, will the temperature change? If so, then the boiling point will also change. Boiling point of water is 100 degrees Celsius, means for the water to boil, you need 100 degrees Celsius. Not anything more, not anything less. So remember, during a change in the state, temperature does not change. Again, repeat with me. During a change in the state, temperature does not change. Again, one more time, repeat with me. During a change in the state, temperature does not change. Now see, let's take, I have a block of ice at 0 degrees Celsius. For this block of ice to convert into liquid water, I supply some heat. It will melt, it converts to liquid water. It converts to liquid water. This is called melting. Melting of ice. You all tell me, melting is a change in the state. Will the temperature change? Will the temperature change? So after all water melts also, the temperature is 0. Maybe after that you can increase the temperature. For all the ice to convert into liquid water, temperature does not change. During this conversion, temperature does not change. Temperature will remain constant. Another example. You have water at 100. You convert it into water vapor. This conversion is called boiling. You all tell me, boiling. Boiling is a state change. Will the temperature change? Temperature does not change. Temperature remains the same. That means this is also 100 degrees. Okay. Now one more step ahead. You have a block of ice at minus 10 degrees Celsius. Possible at minus 10 degrees Celsius, you have a block of ice. Let's take you wanted to bring it up to 0 degrees Celsius. Still it is ice. You just want to bring it down to 0 degrees Celsius, but still it is ice. State change is not happening. Ice at minus 10 to ice at 0. What is happening to the temperature? What is happening to the temperature? Increasing or decreasing? Guaranteed increase. So ice at minus 10 degrees Celsius, to bring it to ice at 0 degrees Celsius, you should increase the temperature. That means you supply heat. Supply heat to increase the temperature. Now it is ice at 0 degrees Celsius. I want to convert it into liquid water. State is changing. Is the temperature changing? Temperature not change. Next, water at 0 degrees Celsius, you want to bring it until water at 100 degrees Celsius. Now, is the temperature changing? Is the temperature changing? Of course, yes. Temperature increase. Now, water at 100 degrees Celsius, I want to convert into water vapor. It is also 100 degrees Celsius. Is the temperature changing? No, there is no change in temperature. So basically, ice at minus 10 degrees Celsius, to bring it to ice at 0 degrees Celsius, you should increase the temperature. Next, ice at 0 to convert to water at 0, you don't increase the temperature. Temperature does not increase. Again, water at 0 to bring it until water vapor, water at 100 degrees Celsius, you increase the temperature. Water at 100 degrees Celsius to convert it into water vapor at 100 degrees Celsius, no need to increase the temperature. What about the heat? Ice at minus 10 to bring it to ice at 0, you should heat it. Ice at 0 to convert to water at 0, still you heat it. Still you heat it. But that heat, you give a special name. What is that special name? What is the special name given? What is the name given to the heat given during a change in the state? Latent. So whatever the heat you supply here, is called latent. Again, water at 0 to bring it until water at 100, you need to heat it. Next thing, water at 100 to bring it to water vapor, you should heat. Here also you are heating. But state change is happening, therefore this heat is called a special name. What's the special name? Latent. So throughout the procedure, you heat. Listen, throughout the procedure, you heat. But during a change in the state, even though you heat, temperature is not changed. During a change in the state, even though you heat it, temperature does not change. Therefore, heat given during change in the state is given a special name. What's the special name? Latent. Other places it's just normal heat. Here it's also heat, but you give it a special name. Latent. Again, listen one more time. During a change in the state, temperature does not change, but still you have to give heat. Therefore, you call that heat, you give a special name to that heat and you call that heat as latent. Then what is latent heat? Heat given to a substance during a change in the state without a change in the temperature. Heat given to a substance during a change in the heat without any change in the temperature. Okay. Okay. So remember the concept. Ice at minus 10, to bring it to ice at 0, you have to heat it, temperature increase. Ice at 0, to bring it to water at 0, you heat it, but temperature does not change. Water at 0, to bring it to water at 100, you heat it, temperature increase. Water at 100, to bring it to water vapor at 100, you heat it, temperature does not change. You see, ice at minus 10 to ice at 0, you heat, temperature increase. Ice at 0 to bring it to water at 0, you heat, temperature does not change. Water at 0 to water at 100, you heat, temperature increase. Water at 100 to water vapor at 100, you heat. Clear? Okay. Right. Now we'll put it to a graph. We'll put it to a graph, temperature versus time. Graph, temperature versus time. What are they telling? No need to look at this one. We'll convert our scenario into the graph. You start with minus 10 degrees Celsius. Minus 10 degrees Celsius, negative part of the graph. Temperature goes to the negative part. Let's say you start with minus 10. This is 0 degrees Celsius. I'll take this point as 100 degrees Celsius. That point I take as 100 degrees Celsius. Right. See, I is at minus 10. You're going to melt it. First, I is at minus 10 should come to I is at 0. I is at minus 10 to 0, temperature increase. I is at minus 10 to 0, temperature increase. Agree with the graph? I is at minus 10 to 0, temperature increase. Agree the graph? Graph upward. Can a temperature increase? I is at minus 10 comes to I is at 0. Now still it is ice. Still it is ice. You want to convert it into water. Will the temperature change? Will the temperature change? On everyone. Will the temperature change? Does not change. That means, can the graph go up now? Graph is in the same position for some time until all the ice melt and finish. Graph is in the same position for some time until all the ice melt and finish. I will write and keep there. Melting is happening. Let's take all the ice have melted and finished. Now you have water at 0. Next you bring it to water at 100. Will the temperature increase? Of course, yes. 0 to 100, temperature will increase. Graph will go up. Agree with the graph? Agree with the graph? Now we have water at 100. To bring it to water vapor, you should heat it. Will the temperature change? Will the temperature change? Does not change. Temperature does not change. That means, can the graph go up? Graph is in the same position. What is happening here? What is happening here? It's happening. Melting, can you see temperature not changing? Boiling, can you see temperature not changing? Other positions, temperature is changing. Understood? Now read the question. Under normal atmospheric pressure, a pure block of ice at minus 10 degrees Celsius was heated at a uniform rate. That means equal amount of heat is given until it was turned into liquid water, and then for some time after, the water started to boil. Which graph correctly indicates the variation of temperature of the system with time? Tell me, what's the graph? What's the graph? First from minus 10, it should come to 0. Then all should melt and finish. Then temperature increases, comes to 100. Answer is answer. Answer is answer. Those who want, write this and keep. First I will put this and keep, right? This is a good flow chart. So writing Dingala write down. Others take a screenshot. Okay. I'll put the graph as well. Okay. Alright. So answer is answer 2. Now we'll go in normal order. Question 31. Question 31. Given below are 4 ways by which zinc metal and hydrochloric acid were reacted at room temperature. In which way is hydrogen gas liberated in higher speed? Hydrogen gas liberated in higher speed. They are talking about rate of reaction. Question 31. They are talking about rate of reaction. We already know rate of reaction increases when the surface area increases. Rate of reaction increases when surface area increases. powder, rate is high. Granule, rate is average. Block, rate is very low. Let's take, you have some powdered reactant, rate of reaction is very high. You have some granules of the reactant, rate is somewhat average. You have block of reactant, a certain reactant, the rate is very slow. So remember, block, granule, powder, rate of reaction increase. Block, granule, powder, rate of reaction increase. A big zinc block, you put in HCl. Powdered zinc, you put in HCl. Where the rate of reaction is high. Powder. Point number 1. Point number 2. When concentration increases, rate will also increase. When concentration decreases, rate will also. Point number 3. When temperature increase, rate will increase. Temperature decrease, rate will decrease. Point number 4. If there is a catalyst, so 4 factors affect the rate of reaction. Surface area, powder rate is high, block rate is low. Concentration, high concentration, high rate. Temperature, high temperature, high rate. Presence of catalyst, high rate. Okay. So they are asking, given below are 4 ways by which zinc metal and hydrochloric acid were reacted at room temperature. In which way is hydrogen gas liberated with higher speed? For the hydrogen gas to be liberated in higher speed, zinc, when you are putting the zinc, you should put a block of zinc or powdered zinc. Block of zinc or powdered zinc. And powdered zinc. Next, you are using hydrochloric acid. You should use hydrochloric acid at highest concentration or low concentration. High concentration or low concentration. High concentration. That means you use concentrated hydrochloric acid. Powdered zinc, concentrated hydrochloric acid. Powdered zinc, concentrated hydrochloric acid. What's the answer? What's the answer? Answer is answer. Okay. Those who want the slide. Can you explain the area part? Area. A block has the lowest surface area. When you make it into powder, its area increases. Why? When you make something into powder, from inside everything will appear out. To break it into powder, from inside everything will appear out. So when everything appears out, area is big. So block has very low surface area. Powder has very high surface area. Higher the surface area, higher the rate of reaction. So block, low surface area, low rate of reaction. Powder, high surface area, high rate of. Yeah, if it is a gaseous reactant, of course, pressure will effect on the rate. So instead of concentration, pressure will come there. High pressure, high rate, low pressure, low rate. That's for gaseous reaction. Right. So here question 31 answer is answer 4. Next question. Between a strong acid and strong base. Now, these things don't get wrong. Strong acid, strong base. What will happen? Neutralization. Neutralization is exo-endo on exothermic. Answer is answer 1. Exothermic neutralization reaction. 31 done, 32 done, 33 done. 34 done. 35. That is actually from hydrocarbon section. Consider the following statement presented regarding natural rubber. It is a linear polymer. Yes. Natural rubber is a linear polymer. It's a linear polymer. Isoprene is the monomer. It is also correct. Rubber is made of isoprene. There are crosslinks among the chains. That is wrong. Only vulcanized rubber has crosslinks. Natural rubber, no crosslinks. Only vulcanized rubber has crosslinks. Natural rubber, no crosslinks. A and B are correct. Answer is answer. Remember, natural rubber is linear polymer. Its monomer is isoprene and it has no crosslink. Vulcanized rubber has crosslink. Corrosion of iron can be controlled by keeping iron in contact with a bivalent metal. M. You can prevent iron from corrosion by keeping iron in contact with a bivalent or metal itself. So that means that metal is preventing iron from corrosion. If that metal is preventing iron from corrosion, that metal is more reactive than iron or less reactive than iron. If that metal is preventing iron from corrosion, yesterday's work, that metal is more reactive than iron or less reactive? And more reactive. So M is more reactive. If M is more reactive, it will undergo oxidation or reduction. If M is more reactive, it will undergo oxidation or reduction. And it will undergo oxidation. All yesterday's work. During oxidation, electrons are gained or released. All yesterday's work. During oxidation, electrons are gained or released. Electrons are released. Released can you write the electrons in product side. Only one thing to learn. Bivalent metal. What do you mean by bivalent metal? Bi means what? B-I, bi means what? 2. Valent means valence. 2 valence. The valence is 2. Valence is 2. Now we'll write the reaction. M will undergo oxidation. That means oxidation number should increase. It's a bivalent metal. That means M will form M plus 2 ion. During oxidation, positive ions are formed. If M is undergoing oxidation, M will form positive ion. We'll write the reaction. M solid converts to form M plus 2 ion. Most of the time it is aqueous. By liberating how many electrons? Electrons are released. You write the electrons in which side? Reactant to product side. Product side. So this is your reaction. See everything from yesterday's session. What's your answer? M converts to M2 plus aqueous, liberating 2 electron. Answer is answer 1. Now you can't tell these are hard, eh? Can you see? Those who felt these types of questions hard before, after yesterday's physics, chemistry night, don't you feel this is okay with you, this section? Yeah, that is cathodic protection. Very good. That is cathodic protection. That is the question. A 4 Newton force and a 3 Newton force are applied on an object at the same instant. Consider the following statement given about the magnitude of the resultant obtained at that occasion. 4 Newton is there, 3 Newton is there. They are not telling the direction. They are not telling the direction. See, 4 Newton and 3 Newton can be applied. 4 Newton and 3 Newton can be applied in the same direction. If they are applied in the same direction, what will be the resultant? You add them on 7 Newton. That is the maximum force. Otherwise, they can be applied in opposite direction. If the two forces are applied in opposite direction, now what's the resultant? Now the resultant is 1 Newton. This is the minimum resultant. This is the maximum resultant. That's the minimum. You add them to get the maximum resultant. You subtract them to get the minimum result. Whatever the other way you apply the force. Now let's say you apply the force like this, like what? Like this. One force like that, 3 Newton. One force like this, 4 Newton. Whatever the other way you apply the force, that one's resultant will be between maximum and the minimum value. When you apply forces 3 Newton and 4 Newton in any other way than these two, that one's resultant will be somewhere in between these two maximum values. You add them to get the maximum, you subtract them to get the minimum, all the other resultants are somewhere in between. Again, I repeat, you add the two forces to get the maximum, you subtract the two forces to get the minimum, all the other resultant are going to be between those maximum and minimum values. What are they telling? A force of 4 Newton and 3 Newton are applied like that. Okay. A, maximum magnitude of the resultant obtained is 7 Newton, correct? 2, the minimum magnitude of the resultant obtained is 1 Newton. Yes. C, magnitude, the magnitude of the resultant obtained always 5 Newton. That is wrong. A and B are correct. What's your answer? Answer number. Correct. 38 question already done. So remember, from this there is something to learn. You add the two forces to obtain maximum value. You subtract the two forces to obtain minimum value. All the other resultants are going to be between those two maximum and minimum. Those 3 points keep in mind. 38 question. That's done. 39. Consider the following statement. Biomagnification occurs along a food chain. What is this biomagnification mean? What is this bio? Magnification means, Nalamai, if you take the food chain, along the food chain from one trophic level to the other trophic level, amount of toxic chemicals that get accumulated increases. Along the food chain from one trophic level to the other, amount of toxic chemicals that get accumulated will increase. Now, for example, I'll draw a food chain. We'll start from grasshoppers, frog, and we'll put another one. I'll write a snake there. Right. If you take grass, in grass there will be little amount of toxic chemicals. Little. Grasshopper, that toxic chemical get added, together with that some more get added. Then here toxic chemicals is more. Frog, That toxic chemical get added, some more get added. Toxic chemicals increase. Snake, that toxic get added, some more get added. Toxic increase. So along the food chain, toxic chemicals will increase. This is called as biomagnification. This is called as biomagnification. Along the food chain, from lower trophic level to the higher trophic level, amount of toxic chemicals that get added will increase. Along the food, from lower trophic level to the higher trophic level, amount of toxic chemicals that get added increase. Biomagnification. Okay. Consider the following statement. Biomagnification occurs along the food chain. True or false? True or false? And guaranteed true. Guaranteed true. Any food chain you take, from lower trophic level to the higher trophic level, amount of toxic chemicals will increase. Biomagnification will take. B. Toxic chemical pollutant concentrate more and more in upper trophic level of the food chain. Correct or wrong? That is also correct. That is actually explaining us about biomagnification. Toxic chemical pollutant concentrate more and more in upper trophic level. Of course, yes. More than the grass, the snake will have a lot of toxic chemicals. So both are correct. Answer is answer 1. Hurry. Question 40. A statement displayed on a board near a tank is shown in the figure. Which of the following human activity in connection with the tank would have contributed most to the change mentioned in the board? What's the board telling? It is you who turned the water in this tank green. That's up onto the camera. It is you who turned the water in this tank to green. Basically, they are talking about eutrophication. Look at the answer. Cleaning the area above the tank. Cleaning the area above the tank, will it cause any eutrophication? Now, what is this eutrophication mean? Growth of algae in the tank. For the increased growth of algae in the tank, there should be nitrates and phosphates. When nitrates and phosphates increase, growth of algae increases, that causes eutrophication. Then that tank will become green in color. When nitrate and phosphate increase, algae growth will be increased. Due to the high growth in algae, the tank will become green color. That is eutrophication. Now see, clearing the area above the tank, will it cause any eutrophication in the tank? No. That increase in algae population, correct lamai. Increasing in algae population due to fishing. Lamai, will fishing cause algae increase? Just think, is there any connection? Very practically thing, you don't need to know biosphere to answer this question. Will fishing increase algae population? No. Fishing is something else. Increasing algae population is something else. So this statement doesn't match. That's wrong. What they are using here doesn't match. It's like you are telling, I ate my lunch because it is raining. I ate my lunch because it is raining. Is there any connection? The increase in algae population due to fishing, there is no connection there. This statement is invalid statement. Third one, accumulation of oil and grease due to vehicle wash. Lamai, when oil and grease get accumulated, tank won't become green color. It will have that oily nature. Smudged like nature. Have you seen sometimes when petrol, diesel falls in the water, you get a smudged nature? That will be only this, not this one. That's wrong. Fourth one, addition of fecal and excretory material into water. Fecal matter, excretory material adds nitrogen and phosphorus to the water. Correct? Our fecal matter, our excretory materials contain nitrogen. Urea is there, uric acid is there. Nitrogen as excretory substances are there. It is adding nitrogen to the water, as well as it adds phosphorus to the water. Oxygen is there. Nitrate will be there. Phosphate will be there. And these are dangerous. If nitrate and phosphate are there, guaranteed algae growth will get increased. If algae growth increases, eutrophication will happen. This is correct. Again see, fecal matter, excretory matter adds nitrogen and phosphorus to the waterway. That means they will have nitrates and phosphates. Nitrates and phosphates will accelerate the algae growth. It will cause eutrophication. Then water becomes green in color. Can't say something. So understand with the reason. Clearing the area above the tank won't cause anything to the tank. Increase in algae population is correct, but due to fishing is wrong. There's no connection. Accumulation of oil and grease to the due to vehicle wash, it will cause a smudged nature, not green color. Addition of fecal and excretory matter adds nitrates and phosphate. When they are added, algae growth will get increased. If algae growth get increased, guaranteed eutrophication will take place. Clear? Perfect. With that, we are finishing off 2020 MCQ paper also. That means 4 papers are done. 2020, no, 23, 24 is done, 22 is done, 21 is done, 20. So now 4 papers are done. Just update me your marks. Update your marks comparing to the previous papers. Compare with the previous papers and update your marks there. Correct. Your full marks for the 2020 paper. Now all the 40 MCQs are done. Hurry. Hurry in. With that, our 2020 O-level paper is also done. Tomorrow you don't have the MCQ night as usual, but tonight I'll be posting the electrochemistry tute. Finish it. Mainly the essay and structured essay question. That discussion will happen on Thursday night. So Thursday night we are not doing 2019 paper. We are doing question discussion from electrochemistry, which is like a continuation of our chemistry night. Hurry. Before we finish, another paper is done. Another paper is done. Another paper done. Y'all tell me, 2020 O-level paper done. At the end, what do you feel? What do you feel? An. Letter by letter. Letter by letter. P. Next. A. Next. T. T. Next letter. Another T. Another T. Last letter. A. A. Next. E. A. S. Y. Part easy. Don't forget the hashtag. and the signature. Okay. Okay then. I'll meet you all again, not tomorrow, day after tomorrow, with the electrochemistry question discussion. Until then, keep working.